Hi, this is Iterative Code 2024 Day 6. I'm Noah Mann. I'm the author of functionalj.io, which is a Java library that brings functional goodies to Java. In this video, I would like to solve Day 6 puzzle using functionalj. Here is the highlight. Part 1. We are going back in time to 1518 to the North Pole Prototype and Suite Manufacturing Lab. But we need to be careful of the time paradox. So we need to make sure that we avoid the guard. There is a single guard. We will be given the map of the lab where the sharp symbol is an obstacle. And this symbol represents a robot guard that will be patrolling the lab. In this case, it's looking up. So the robot will be moving up along this line like this until it hits the obstacle. Once it hits the obstacle, it will turn right always and keep walking until it hits the obstacle. And then it will turn right and keep walking. It will stop walking when it walks out of the lab. We need to make sure that we can determine how many of this cell that the robot guard will be walking through so that we can avoid it and not create a time paradox. This type of problem doesn't have algorithmic solution. We need to simulate the walking of the robot guard from the beginning until the end. And that means we will need to parse this map, figure out where are all the obstacles, figure out where the robot guard, and as time ticks, we will move the robot guard and follow the rule. When the robot guard walks out of the board, the simulation will stop. We need to count how many of this cell that the robot has passed. In this case, all the X's are what it has walked past. If it walked past the same cell, we just count it as one time. Count how many of them, and that's the answer of this puzzle. You can see in this animation. So as it goes off the screen, we count how many of those cells it's walked through. Let's see the code solution. As you see that we need to simulate the movement of the robot guard. To do that, we need to involve a lot of things. For example, the movement, the direction of the robot, the position of the robot, the grid in which obstacles are, as well as the logic to walk along from the beginning to the end, as well as the logic to collect the visited cell. Object-oriented, it's a good paradigm to organize the code so that code that are related to the data is working on close to the data. So in this case, I use the mix of object-oriented, that's procedural. Of course, we will try to do it with functional style as well. So there are certain code that are specific or involved directly to direction. For example, the direction has a symbol like up, right, down, and left. Direction has the next row or column that will go through. So this direction object will hold those information. We can also get the direction from the symbol. So that way we can look at the grid, see the character on that, and then get the direction out of it. The direction also involves turning right. We also have a map between directions to symbol. So this way, we can going back and forth. If we have direction, we can get the symbol. If we have the symbol, we can get the direction. There are also codes related to the position. So for example, sometimes we will use row and column, but sometimes we want to use position. So we should be able to check whether or not the row and column is at the position. We also want to move. Given the direction, we want to move to the next position. There are logics related to grid. Given the grid, we want to figure out where the starting position and the starting direction. We want to find a way to get character at the position. And of course, sometimes we need to use row and column. So we have both of them there. If the row and column go out of bound, we want to return out of bound. If it hit the starting position, because we could not change whatever we get from this input map. In other words, the lines, we mask the start position that instead of this symbol for the robot guard with the ground. Otherwise, it's just whatever on the ground, if it's obstruction or whatever that is. We also have a logic to figure out the starting point. Then there will be a logic to walk the robot guard. So I call this a grid walker. Because it is possible that the robot will walk into infinite loop, there will have to be a way to detect that situation. In this case, the important logic will be in walk step, which process the position. If the position is out of bound, it return the out of bound result, the out of bound state. If it not, get the symbol and see if the symbol is the obstacle. If it is, it will turn right and then return the state. If it's not a obstacle, the position will be the next position. I'll return the next state. So as you can see, this is an iterative or a procedural programming. Then we need to save the state into a set of visited states so that if it repeats, we know that we gone into the infinite loop. The reason why we use state rather than position is that even though the robot guard are on the same position, if they are not turning to the same direction, we don't really care. It will not going to go in infinite loop. Only when it's in the same position and turn to the same direction, we will get into the infinite loop. If that's the case of infinite loop, we return now. Then there is a logic to convert this iterative or procedural code into functional. In this case, to return the stream. In functional J, stream plus is an enhancement to stream. It behaves just like stream, but more method to it. So to do that, we start with generating the stream by repeatedly calling step. So the first element we call step, and then the next element we call step again and again. So the robot will be walking and walking. And we will do this until the state is now. So we accept while it's not now. So we will stop until it's now, right? So that means if it's repeated, if the infinite loop is detected, it will return now, so it will stop. But we also want to stop, even though it's not in the infinite loop. We also want to stop when it go out of bound. So we will drop everything after we detect that the state is out of bound, meaning that we will keep the state that is out of bound. The first one that is out of bound will be cut. And because the step only start emitting the state after it start walking, we will need to insert or prepend the first state into the generated stream as well. So in this way, the stream will start with the first stage and then subsequent state from all the walking. The last chunk of logic will involve counting all the visited block. Grid is created from the input lines, and then we create a grid walker. We'll ask the grid walker for all the steps, and then we exclude the state in which it go out of bound. Then we'll get the distinct position and count how many of them are there. And that's what the puzzle is asked for. That's it for this. So as you can see, there are a good mix of procedural, object-oriented, and functional. Procedural are here where we do a loop, keep calling things. Object-oriented is when we put the logic closer to the data it's operate on. And a lot of functional here, you can see things like find the start position, or this functional looking code. The conversion from procedural into a more functional. We can see more of functional code here as well. Functional J allow us to write more functional code, but we can mix and match it with the existing Java style of code like procedural or object-oriented. So you are not forcing to use functional style only, like when you move to other languages like Clojure or Haskell. That's it for part 1. Let's see part 2. For part 2, we want to change the strategy from calculating the path or the visited cell by the guard by putting an new obstruction into any cell on the grid. and make the guard stuck in the loop. So let's say if we can put a new obstruction here, the robot will walk up here, 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 and here up into the loop. And we want to know how many places we can put the obstruction and the guard will go into a loop. You can see here there are at least 2 ways here in this picture. You can actually put many more. For this small example, there are 6 places where a single obstruction can be put so that the guard will move in the loop. How to solve this? Unfortunately, we need to brute force this because this problem originally in part 1 is a simulation problem. There's no algorithmic way to solve it. So it's not easy to determine where to put obstruction algorithmically. So we need to simulate that again. So we will try to put an obstruction to one of the cell at a time. Try them all, but try one at a time, and then see if the robot get into a loop. Let's see how this is done in the code. Here's the code for part 2, which extend the code from part 1. Because we already have the grid, which can give us the character at the row and column. Well, and we want to be able to add an obstruction or an obstacle at a specific location. So we extend the grid into the grid with obstacle. And then it will have the position of that obstacle. If the caller is asking for a character at that location that match the obstacle, we will return that we found an obstacle. Otherwise, we just forward this to the grid. Then, in order to check whether or not the robot get into a loop, we create a walker for that grid and then step through it and see if there are any stage that is out of bound. If there are none, that means the robot get into a loop. Because if they go out of bound, they are not in the loop. In order to count them all, we will loop the double loop from 0 to height and from 0 to grid. So that is a convenient function to do to range. And then from row and column, we map it to position. And then from the position, we use that as the obstacle. See the obstacle to create the grid with obstacle. And then we check whether or not the guard will move in the loop. And then we count all of them, all of the grid that has that condition. As you can see, it calculates the example map very quickly. It takes more time calculating the prod data. It takes 8 seconds to carry prod data because it brute force and the grid is big for that prod data. That is it for day 6 puzzle. I hope I showcase the capability of functional J, particularly in this problem, the mixed use with OO and procedural code. If you find this useful, please click like. If you want to see more, please subscribe. Either way, thank you for watching. See you next time. Bye bye now.